All right, shout out to my boy Crispy Chicken who is asking about um, this website called Alternative Physics. Oops, did I pull it? Yeah, there we go. So asking about this website and the experimentation that they provide for evidence of time dilation in support of relativity theory. So he asked about these specific questions. Um, Clocks on orbiting satellites move slower. Atomic clocks on planes move slower. The Michelson-Morley experiment, muon particles decay more slowly when falling. And finally, in regards to whether or not the vacuum tubes in the Michelson-Morley experiment were made a difference or not in the detection of the ether. And in this case, they did not. Um, didn't matter. So, and I'll get into all of that or in order, starting from clocks in orbiting satellites move slower. So, any clock in motion moves slower, loses its tick rate. It experiences electromagnetic retardation. This can be this, this can be caused by various reasons, but mostly it's moving through a magnetic or electric field that will shorten or what's it called? Well, it'll retard the wavelengths. Really, is what I mean. That's exactly what it's called. So that shortening of the wavelengths will cause the clocks to go out of sync. And if you're familiar with how an atomic clock works, what they have is a magnetic field that keeps an excited atom, whatever that is, particle, wave, it doesn't matter. It keeps it in an excited state where it's vibrating, and it naturally wants to its vibration wants to equalize, right? It wants to stop vibrating. So what they do is they use the magnetic field to calibrate it out. They shoot a radio wave in the middle of it, to keep it excited, and they keep it within that within a quote unquote stable state of decay, and they measure that vibration frequency to get really precise measurements of time. So that process, even while they're stationary, the clocks go out of sync. They have to be kept in constant corrections to maintain any accuracy. So and then in addition to that, when the clocks are in motion, they experience additional um, electromagnetic retardation, and that's noted here in the Heffel and Keating experiment, which is where they first tested this and came to the conclusion that relativity theory was supported by this. So what they have here is how much their clocks went out of sync before and after their east and westward trips, and the relativistic predictions here. And what I have on the next page of this is the summary of what they first posted in 1971, and then in 1972 they re-released their findings with post calculations, corrections, and data massaging, and everything suddenly fit within the relativistic corrections. But the clocks went out of sync so sporadically in the experiment that the only thing that this experiment proves is that moving clocks move out of sync, because the way that they came out of sync um, to each other was way outside of the scope of what they had originally predicted by how much it would go. So like there's no real discernible data that they could get from that, but they go ahead and put it forward as time dilation evidence. So before we close out on the atomic clock corrections, we have Paul Marmot here. Um, Open and not on the page already. Let's see, is it up? So atomic clocks are also corrected for the Sagnac effect, and this is just the this gets into the preferred direction, right? So what Michelson-Morley originally measured and all that, they atomic clocks, yeah. So they use this equation here to correct for the Sagnac effect, which is basically how they keep their clocks in sync. So in Heffel and Keating here, the clocks were coming out of sync to varying degrees. They couldn't figure it out. Well, it turns out you accounting for the Sagnac effect is the way to do it, and the way that the Sagnac effect is calculated. Second. Sorry, I didn't have this pulled up ahead of time. Anyway, it's just the delay in the speed of lay is proportional to the observer's velocity, basically, and the observer being somebody with a GPS receiver in a car that's moving, or someone that's or an interferometer that's spinning, right? The rotation um, that that movement is going to cause a delay that's proportional to that rotation or to the linear motion too. In 2004, that was shown by Ruyang Wang that the linear motion also contributes to it as well, which is why they say in Michelson-Morley that it was a null result because they can't measure the linear motion and all that. So that's how they get out of it. They don't actually make any claims about a refractive index or vacuum medium or anything like that. So let's see here. Oh, Sagnac, GPS equation, or not GPS, Sagnac equation. Yeah. Okay, so yeah, how they derive how much fringe shift pattern would be. So it's 4 times the angular rotation times the area of the device over c squared. And this is just, the rotation of the device times the area. So how far the length that the path of light and or the fiber optic cable is. And then for the linear speed, it's 2 times the velocity times the length. So it's just the big key part here is this is just movement, the motion, right? Linear motion and rotational motion times the length of the device. So that's all they're doing to make the correction. So we're told that these atomic clocks have to account for time dilation, different gravitational potentials. Nah, they just have another equation that accounts for the Sagnac effect. So this looks all confusing here, lots of different variables and letters and all that. But I forget where it is, not fully prepared, but he mentions here that that equation in 13 is just a dressed up version of the Sagnac effect that accounts for it on the exact same level with no relativistic corrections necessary. So when they keep GPS time in sync in that regard, and then, the assumed speed of light being a fixed speed, there should be no invariant transformations of the distances derived under how GPS is set up, but it actually shows that GPS, there is a delay in the speed of light, and it's proportional to the velocity of the observer, and that's also noted in here from the Around the World Sagnac experiment. So you know how we were just discussing the issue of the vacuum, and it wasn't done in a vacuum. Well, there was an experiment done in the late 90s or early 2000s called the Allen and other Sagnac GPS what was it called? The Allen and others Around the World Sagnac effect in GPS or something like that. But anyway, what they found was that there was this delay, and it's about 0.014 microseconds going east to west faster and slower going in the opposite direction by the same amount. And what they attributed that to was the physical rotation of the Earth. But in 2004, Wang showed that that's not the case. There's no Earth rotation, and the effect isn't due to rotation. And secondly, let's say hypothetically that the Earth is rotating and that that GPS is accounting for this discrepancy due to the rotational effect. It still doesn't. GPS still wouldn't be accurate then, because an actual moving observer outside of the confines of Earth rotation, right? So if you're going 30 miles, an hour, the accuracy of GPS is going to be reflected. The inaccuracy in GPS is going to be reflected in that measurement, according to how they have it set up. But it shows that, but because the speed of light is proportional to the delay of the observer, or to the velocity of the observer, it accurately derives their distance with no corrections necessary. Accounting for that varying speed of light, and that's what's actually making GPS so lethally accurate. Let's see. So anyway, sorry, I kind of got sidetracked on the Allen and others Around the World's experiment. So when they did that, presumably in a vacuum, right, in space, right. So by their own metrics, they have the conditions where they've used GPS satellites, whatever configuration they're in, as a giant interferometer, and they found the exact same results as Michelson-Morley. And it should be noted too that the Earth's motion around the sun being linear and the rotation being a linear speed, those should be added together if that was what's truly being accounted for in GPS, but it's not. It's literally just proportional to like normal speeds on Earth. It's not nothing crazy. So anyway, we got the atomic planes. We covered that. We covered atomic clocks. So we got Michelson-Morley's. Let's see. So for Michelson-Morley, so they came up with a way to, let's see here. Let's pull up the history of interferometry real quick. And then we'll close on muon particle. Actually, we'll just bang this one out now. So muon particle decay, they came up with a special detector to detect these muons. They have a prediction about where muons would potentially exist in the atmosphere or something because they're, being shot at us from space or whatever, cosmic energy and all that. So they have a prediction about how many they should see based on their, alleged decay rate and all that. And when they use their detector, they detect more muons in areas where they couldn't possibly be if their theories about them are correct and all that. So they attribute that to time dilation. It's a reification fallacy. It means nothing. And let's see, is Michelson-Morley up yet? Yep. Okay. So for Michelson's and Moore's, this is the fringe shift pattern that they were expecting to get. So they were expecting to get a reading of about 5 fringes, which would have equaled 30 kilometers a second. Each fringe under the metrics that they came up with to interpret the results was every fringe was going to be about 5 kilometers a second. And they got just over 1 fringe. And keep in mind, they were in a basement. And what was the other factor? I can't remember. I think for them it was just in basement. Their apparatus was open. They didn't have vacuum tubes. I don't even think they had tubes, to be honest with you. So they were able to produce a 5 kilometer to 7.5 kilometer fringe. They were just over 1 fringe, like I was saying. But then that's when Dayton Miller came in with the refinement to all the interferometry experiments, and he used a Michelson-Morley analogous device. And he actually, in later experiments, he actually inherited Michelson's old device when he was doing these at altitude. So what he showed was, or what he hypothesized and then experimentally showed, was that when you do interferometry experiments below sea level, like in a basement in a lab, behind concrete walls and all that stuff, you're interfering with the ether wind effect. And further, when you adjust the arm lengths or put it in vacuum tubes and then or put it in tubes that have a medium in it so that they can account for the refractive index. So by the way, the refractive index argument that's not a real argument. It's like a coping mechanism because they can do them in a tube that has a gas in it of a known, what is it called? Refractive index. So they can account for these factors in that regard, and that's how they do that. So they do the same thing in fiber optic cables. The refractive index is already factored into it. So that's not the issue. The speed of light doesn't actually change in their medium. It just takes longer because it's traveling through different. It the path it takes is longer, so to speak, is what they're saying. They're not saying that the speed actually changes. So anyway, so yeah, what he found was that Shanklin's bases. So yeah, when they mess with the medium of the tubes, when they mess with if the apparatus is at sea level or not, or above, when they use certain metal shieldings for the pipes as well, it all messes with it. But what Dayton Miller did find is that different radiant heat sources didn't really affect it at all, and that's the big criticism of his work is that he didn't account for temperature differentials and stuff. That's not true. Oh, this is the picture I was looking for of his outpost as well. So this is his observatory that he made. So as you can see, it's open, got free flow of air. It's not as obstructed as being in a concrete basement, 250 feet underground and all that, or below sea level. So when he went to altitude, he got much stronger readings. I think his were around 8 to 10 kilometers a second, and he was able to, when you plot his measurements against sidereal time, it shows fluctuations corresponding to the equinoxes where the measurements reach their minimum and maximum dimensions on the equinox to the day. So in other words, measuring the movement of the sun. Now, Miller's interpretation, obviously, is through the heliocentric paradigm. So what he thought he was measuring was this, but just at a slower speed than the 30 kilometers a second. But what was actually happening is this. So the sun's moving over top of us. We have our perspectives over here, so we see it, looking, doing its thing, and that's the measurement that Dayton Miller moved. So as the sun's in the northern hemisphere, Alexander Gleason estimates that it's moving about 900 miles an hour, something like that, to close to 1,000. And then when it goes in the southern hemisphere here, it starts picking up speed. It goes about 1,100 to 1,200, is what Gleason says. And that speed fluctuation to maintain the 15 degrees per hour is what Dayton Miller measured to the day on the equinox. And then after that, after Miller, right? We got where is ether wind? Nope, that's wrong one. Ether wind. Okay, so after Miller, we have Yuri Galev doing Michelson-Morley with optical wave bands and millimeter radio wave bands, reproducing Miller's experiments, showing, let's see if I can pull it up right here. How cool would that be if it was on the right page? Nope. So yeah, his fringe shift patterns were doing the exact same thing. He literally reproduced Miller's work, literally reproduced it in 2002. 2004 was when Wang did the generalized Sangak effect and showed that there is no, or I'm sorry, that the fiber optic gyros can measure linear motion, and therefore Michelson-Morley results have to apply without any second order corrections. And second order corrections meaning time dilation and length contraction. And then your boy Hector Manera reproduced Michelson-Morley in 2004. And I think that was it. Who else did Dayton Miller? I thought there was one more Miller lad. Can't remember. We actually did it twice. I think Pruner DeFore also did it as well. So, yeah, so Dayton Miller did 5,200,000 measurements, and all his data shows that it matches that the fringe shift pattern matches sidereal time, meaning that the translation of motion from the sky is being measured there. And Yuri Galev also did it. So I hope that answers all your questions. And I'm going to go ahead and wrap it up here. Let me double check this. So muon particle decay, they're also blah. So, all right. I think that was everything. Thank you and have a good day.